I want to welcome you all to the 205th or 206th Earth2Class program, at which point we always say it seemed like a good idea at the time. Now at least we get to sleep in a little bit later on Saturdays. But today we're very pleased that Dr. Sid Hemming is able to join us and talk about some of the ice-rafted debris studies she did on IODP Expedition 382. Let me give you a little bit of an introduction. Somewhere in here is my slideshow. Okay. So the purpose for today is to understand the geological history of Antarctica using sediments melted out of icebergs. And these are some of the participants from 382. This is Dr. Brackfeld, who may be joining us a little bit later. These are some of the ice-rafted pebbles that she found in one of the cores, which she marked for study. This is much of what they saw from the ship between March and May. Right, Sid?
Yeah, we saw a lot of those. A lot of those, they ran us off the sites a few times too.
I don't know, I always figured that we could be tougher than icebergs.
Yeah, not, you know, we had a, you know, we had an ice watch person and several times we had to abandon our site and come back to it. And
right.
It's tracking where the icebergs are, and 2 or 3 times it actually literally went right over the site that we had vacated.
The ship is tough. It got through the perfect storm, but it's not that tough.
Right.
Not invincible. So here's a picture of the ship. This is the bow of the front. And in these areas, they reserve it for taking pictures and also for Sunday barbecues. Did you have barbecues in the cold?
We did eat outside at least one time, but actually I think it's on the weekends if the weather is nice enough. They do.
Yeah, on Sundays they have barbecue.
Yeah.
And the ship is about 430 feet long. The derrick is about 200 and something feet high. We calculated one time that if it were coming into New York Harbor and there was nobody standing at the top of the derrick, it would be able to get underneath the Verrazano Bridge.
At low tide?
At low tide. At low tide, yes.
It's like the Queen Mary.
Right. And some of you remember a few years ago, in 2006, I believe, they deconstructed the ship down to the keel, and then using modular construction, they put back everything. So all of these little sections in here can be taken out and replaced with something else.
Oh.
This is a picture when the ship was in port in Curacao a few years ago. These were people who were on what was called a School of Rock expedition with me. And if you go and look at the view of the slideshow on your own, you can click on some of these videos and learn a lot more about the ship. So here are some of the sites that were drilled and the dates they were drilled. This is in the area between Antarctica and South America. And just a little bit about Antarctica. It's divided into East and West Antarctica. This is the prime meridian. This is the international date line down here, 0 and 180 degrees. We have a variety of ice shelves, like the Ross Ice Shelf in West Antarctica, several ice shelves in East Antarctica. And at various times, bits of the ice will break off and start flowing through the Antarctic circumpolar current, which travels around Antarctica and keeps the ice, in many cases from Antarctica, from floating farther northward. I'm not certain any of the ice from Antarctica goes up into the South Pacific or South Atlantic, does it, Sid?
Rarely.
That's what I thought. Might be little eddies that come off like this. But sometimes we get ice on the ice shelf, which gets covered with rocks that have been carried down. And as the ice is floating around Antarctica, it will melt. The rocks will settle down to the bottom and may occasionally be picked up in the cores that are collected. These are called ice rafted debris, or IRDs. And part of what Sid's going to be talking about is the studies of this material, trying to track it back to its source origins on Antarctica. Same thing happens up in the North Atlantic. A lot of IRDs are tracked back to source areas there. Here's an example of one core with Pebble from a IRD. And with these studies and others, geochemical studies, we've been able to reconstruct to some extent the climate history of the past 65 million years. And we have something called the Eocene Optimum, which was around 50 million years ago. This is when many of the modern mammals began to develop. But then Antarctic glaciation began about 35 million years ago. And it wasn't just a drop into cold and then stay cold. As you see, it went up and down. We have an Arctic thawing period, then a reglaciation period, and a variety of rapid glacial cycles, many of which we're able to interpret from the ice rafted debris. So here's a picture of some of the scientists on board the ship. These are the two chief scientists, Mo Ramo, who's now the acting director at Lamont, and Mike Weber from the University of Bonn in Germany. With them is Trevor Williams, who used to be at Lamont. He's now at Texas A&M. And when I move this, you have a picture of a humpback whale who came to play one day. Okay, I'll stop my screen sharing. Step
Okay,
over there.
I'll start mine. So
Go on, Sid.
shall I just go ahead and get started?
Go ahead, and we'll let everybody know if you have questions. You can either use the chat feature and raise your hand under the reactions, or you can just pop in.
Okay, and I'll try to pay attention. Right now it's showing up on my screen. Somehow or another it comes and goes. So just holler. Okay, so what I'm going to do today, I think maybe somewhat similar to what Stephanie presented a few months ago, or right after we got back from the 382 cruise. But I'm not going to be only focusing on 382. I'll talk about some first results from 382 right at the very end. But I sort of want to take you through a little bit of the background as I see it towards really using these kinds of methods to understand the past ice sheet history in Antarctica. And this photograph is just a photograph under a microscope of a sample that's been sieved and washed. So this is the sand fraction from an actual sediment sample from around Antarctica. And so you can see that there's some variety in the different minerals that you can see and we typically pick the hornblends right under the O here and deposited. And if we find micas like biotite up here, we would pick those as well. And this general study of Antarctic provenance involves a large number of collaborators, including Stephanie, who's here. In this presentation, Trevor Williams and Tina Vanderflirt, who've been collaborators on this from pretty much the beginning of my becoming interested in Antarctic provenance, and Kathy Licht, who's been a really close collaborator probably for the last decade. And our students are going to be sort of featured in this presentation, but this is it's one of these really fun kinds of collaborations where there's so many people that I couldn't make a list that was comprehensive, and it would still be too big to show here. So I'm really presenting the works of many other people in this talk. And in addition to being really great collaborators, Tina Vanderflirt and Trevor Williams are both also really quite good artists. And so you'll see slide from Tina or slide from Trevor in a lot of these, because I just lifted really nice slides, better than I could have put together from previous talks that they have given. So one of the big motivations for understanding the past ice sheet history in Antarctica is that there's a lot of ice on Antarctica. If you take all the ice on Antarctica together, it's something close to 60 meters sea level equivalent of ice. So if all the ice were to melt from Antarctica, sea level would rise by that amount. There's a few kind of important things to take note of from Antarctica. One of them is that West Antarctica is a much smaller part of the ice sheet with only something like 5 meters of sea level equivalent and thinner ice, but a lot of the ice is grounded below sea level. So the map on the left here has elevations where sea level is close to white, and above sea level is in the reds, and below is in the blues. And so you can see that a large part of West Antarctica is actually grounded below sea level. And that's one of the reasons why the West Antarctic ice sheet is considered to be particularly vulnerable to global warming. Another one is basically how the ocean currents flow, and warm subsurface water is actually flowing up into those low-lying areas under West Antarctica. In East Antarctica is much bigger, 52 meters more or less sea level equivalent. I mean, these things are estimates, and I'll show in the next slide, I'll show like an updated estimate on the thickness distribution. But most of East Antarctica has the ice grounded above sea level. When I say most of East Antarctica, it's a big place, but you can also quickly see quite a substantial area of blues, whites and blues under East Antarctica as well. So most of it is grounded above sea level, but there's a substantial portion. And one of the things that I'll be sort of featuring today is the vulnerability of this part, the Wilkes Land coast of East Antarctica. So on the left-hand side, this is topography, elevation, and on the right-hand side is a map of the ice thickness, and the drainage divides are these dashed lines, and the dark sort of things that look like rivers are the major ice streams that are flowing, that are the quickly moving ice from the continent into the ocean. And then this is just an updated, beautiful map from a recent paper called Bed Machine that has a recent sort of reassessment of the ice thickness all around Antarctica. And you can actually, just from the ice thickness, you can actually pick out some of the features of where the ice thicknesses sort of penetrate in as thin zones is where the big ice streams are draining out of the Antarctic ice sheet. And this is just so, I think I'm going to give Mike this, I guess you have the video anyway, but I'm going to want to make the information that I'm talking about available. So that figure is from this study from Morling and al. 2000.
Okay, I'll see if I can get it uploaded to the website.
Okay, so what I'm going to do now, from this same paper, there's a video, and hopefully this is going to work. What I'm going to try to do is to just, I can try doing it from the link. I put the link here so you can go back to it. But what I'm going to do is stop share, and then try to go to the actual link. And I'll just apologize ahead of time. I debated about going to the trouble of getting the Prime, the better version of YouTube, so that you don't have to watch ads. So I'll apologize for whatever ads you're going to have to watch right now, because I didn't do that. But I watched this video and I thought it was really pretty cool. So can I make it full screen?
Looks good.
So this is one of the prime places of study of Antarctic glacier activity, the Thwaites Glacier right now in the Amundsen Sea, because it's one of the places that's considered to be the most vulnerable. And this is the Ross Sea. You're coming up into the Trans-Antarctic Mountains here. And the ice stream that they're peeling back to show you, this is the Bird Glacier, and the relief between the top of that mountain and the bottom of Bird Glacier, I believe, is the biggest relief on Earth. If it's not, it's very, very close to that, coming down the beautiful Trans-Antarctic Mountains. This is just sort of a tour around Antarctica, and then they zoom in and go under the ice in a few kind of key places. So you can see deep trough. This is the David Glacier, and you can see the really deep trough right at the end of the David Glacier.
Are these glacially carved, or are they the result of lower sea level and river?
They're glacially carved. I mean, I'm sure there's other factors involved, but the really deep holes are from the glacial carving. Actually, Stephanie has been on cruises to collect samples off of Nina's Glacier, some of the Denham Glacier, several of these. Stephanie can speak up and tell you. I haven't gotten to go over here, but I still think this video is pretty awesome. There's a really, really, really deep trough, Denman Glacier. I believe this is the one that sort of hit the news from this scientific article, because it's the deepest gouge in the Earth. Is that right, Stephanie?
That's a good question. I don't know.
I think
for sure. The deepest continental gouge.
Yeah, from the continent. Yeah, I'm pretty sure it was. I hadn't appreciated it until I found this video and saw the sort of the news blurbs. I think if you had asked me before that, I would have said it was birds. So I was actually a little bit surprised. So, and this is the Recovery Glacier. This is going to feature a little bit later when we talk about the Weddell Sea stuff. It's also a really big outlet glacier from Antarctica. And then this is just sort of zooming out with the ice removed to see the topography on Antarctica, and then cover it back up with ice. So one of the issues that we have, of course, with trying to understand the history of the Antarctic ice sheet is that the ice is on top of everything that we'd be looking at. And that sort of features in my sort of trying to understand how to work out what's under the ice. So this is a cartoon or a reconstruction, and the source for this is on the bottom right. And this is basically the reconstruction, reuniting Gondwana land. So this is based on a variety of different kinds of geological and geophysical observations. And I'm just letting it play a few times so you can see. This is just a repeated, I guess it only goes a couple of times. So here's Antarctica, but really kind of a central figure in the Pangea reconstruction, and South America, Africa, India, and Australia, and sort of note where they're connected around Antarctica, right? So this is the Weddell Sea today. The Antarctic Peninsula sort of points up towards South America, Drake Passage. This part of Antarctica, the Droning Maudland area, was connected to Southern Africa, and India and Africa and Antarctica were kind of, there's a lot of continental mountain building that's called Pan-African about 500 to 600 million years ago. And Antarctica was already connected to Australia during that time. And so we'll see when we look at the age distributions that the ages in this part of the Antarctic continent are actually older than they are around most of the rest of the Antarctic continent. We've got some really old stuff, the old cratons. Craton is the stable continental interior in South Africa, and Antarctica show, you can see those as well, but big area along this Wilkes Land coast that it has old sources. And for me, one of the hardest things about getting used to studying Antarctica was learning the place names. And so I'm just going to go through and say them and try to be careful about pointing out the place names as I blurt them, but feel free to stop me if I say something that seems mysterious because you don't know what place that is. So this WS stands for Weddell Sea. This is Droning Maudland. This little indention is Pritz Bay. And this is Wilkes Land and Adelie Land that were connected to Australia. And GM stands for the Gamburtsev Mountains. The Gamburtsev mountains are entirely buried by ice, but it's a large mountain belt and really kind of enigmatic story. And so it's one of the things that really focused research attention during the most recent International Polar Year. I can't remember exactly what that year was. I want to say something like 2005, but more than 10 years ago, there was a big sort of geophysical program to try to better understand Antarctica. TAM stands for the Trans-Antarctic Mountains. The Trans-Antarctic Mountains essentially split East and West Antarctica from each other. And this TAM is not really quite located right on this diagram. And then MBL stands for Marie Byrd Land, and WA stands for West Antarctica. And then I'm not going to repeat all those things again, but I just, for the place names, I just pulled up a map from the Wikipedia that has the permanent research stations from the different nations around Antarctica. So as you probably already know, nobody owns Antarctica, and there's an Antarctic treaty to protect Antarctica, but there's many countries have built research stations around Antarctica to basically keep their association, but also to study this really kind of remote and wonderful place, both for the earth sciences, the biological sciences, and it's also a really good place for space sciences. So a couple of years ago, Kathy Licht and I put together a review of basically how to go about looking at the sediment provenance from Antarctica, given that it's so covered with ice. And so this figure from our paper is a combination of what's been mapped for the geology, and these colors on the left-hand side here are the legend for the colors on the map for different ages, and it's overlain on the bed map topography, not the latest version that you just saw in the video, but the bed map version below, but before that one. And it has the ice divides that I called out in that first diagram. This is try to put everything together with what we want to do is use the geology, the old ancient bedrock geology, as a means of having natural tracers of sediments that would be deposited in the ocean as a result of the movement of the ice sheet and dropping icebergs into the ocean. And so you can see kind of immediately that it's not one sector has one color, but you can see that there's a tendency for the rocks over in this West Antarctica side to be, this goes from old on the top to young on the bottom, unfortunately. The rocks over here on the west side to have colors that are towards the bottom here, and for the rocks over here on the east side to have colors that are towards the top on this legend, right? So older geological terrains in East Antarctica compared to younger geological terrains in West Antarctica, and this sort of brown to green color is pretty common in many parts of Antarctica, but it's particularly common along the Trans-Antarctic Mountains. And just in case you want to explore for yourself, this site, this QGIS came out after Kathy and I had finished our paper, but this is comes from the Polar Geospatial Group in Minnesota, and this is called Quantarctica, and it has many layers of the different things, like I think it has the newest bedrock elevations now. So the bedrock elevations, the ice thicknesses, the geology, all these things are sort of put together in layers in this map, and so you can use that as a really great reference tool. Okay, hold on just a second. I see there's 3 things in the chat. Would that be considered a fjord? It would have been considered a fjord. So a fjord is actually a place where the ice goes into the oceans. And so there are some fjords around there, but where those really big trenches are, when sea level would be higher and the ice would be further back, that would definitely be a fjord feature. And then how were the mountains formed? Is this the Trans-Antarctic Mountains you're talking about? Richard?
Anyway, I guess any of them through continental collision, I'm not sure.
Yeah. So continental collision is a really good way to form mountains. The really big mountains in Antarctica, the Trans-Antarctic Mountains, are actually a little bit enigmatic, but they're located at the boundary of a major rift basin. I guess you'd call it a rift basin, the West Antarctic Rift System. And so it's thought that the really high mountains there's been a lot of history prior to that, but it's thought that the high mountains there are somehow related to that major rifting process. So there's
Like
also, sorry,
like the Mid-Atlantic Ridge.
well, it would be more like the Basin and Range Province in the Western US, or the East African Rift System.
Okay.
So there are really, pretty substantial mountains associated with, even though it seems counterintuitive because extension leads to thinning of the crust. And so maybe you would think everything should be lower, but the relief that's produced by that is really great, and the upthrown block actually moves up. So the process of rifting produces really pretty high mountains. But having said that, that's a really sort of a generalization. That's the association that, the best association for the Trans-Antarctic Mountains, but exactly why they're so big and so prominent like that is still a subject of study, I think.
Right. Let me just ask one more thing. Then would there be very little erosion because they're protected by the ice? There's no, they're not
Yeah,
exposed.
that's a really good question. Most of, actually I took out the part about, the evidence for how slow or fast things are eroding from this. But yeah, they're mostly, in most of all of Antarctica, the erosion rates are extremely low. And in the Trans-Antarctic Mountains where they're not the major ice streams flowing through the mountains, those big troughs like the Berg Glacier that we looked at, that's a place where erosion has gone very, very deep. But most of the transect along the Trans-Antarctic Mountains, the erosion is mostly low. And it looks like that it's one of the chicken and egg questions that we're trying to get to the bottom of. But there's low temperature thermochronology evidence for a rapid incision event very close to the time of the initiation of Antarctic glaciation at the Eocene Oligocene boundary 35 million years ago, like Mike was talking about. So the question, and that's not so different than the initiation of the major West Antarctic rift system. And so the question becomes, what part of this is tectonics and what part of this is glacial erosion? But the glacial troughs that are cutting across the Trans-Antarctic Mountains in a few cases have created really, really quite deep troughs well below sea level.
Thank you.
All right, so this is another movie that I hope goes, but this is this is a model for the location of the ice streams starting from the 25,000 years ago towards the present. And the color bar, the legend here, this is the surface velocity. And so you can look at this and see the sort of black, really dark areas are approximately the same as what we looked at with the glacial divides in the couple of those maps. And the really sort of bright colors, the yellows and reds, are the places where ice is basically streaming off the continent very, very quickly. And that's not so different than what I showed you for the modern ice velocity. So, but this is starting at 25,000 years ago. You can sort of see that you can't quite see all the nooks and crannies that you can see today because the ice was more extensive then. And this model goes from 25,000 years ago to today. And it's a model. It's taking into account to the best it can the bedrock topography and the physical characteristics that erosion depends on: the basal shear stress, the ice velocity, the sediment thickness. And this comes from a paper from Gallage et al. In 2014. So let's hope. Oh, there it goes. So one of the things that's really exciting for me and people like me and Stephanie, when you see a map like this or a movie like this, is that the positions of those really bright areas is not constant through time, right? As the ice changes from its LGM, last glacial maximum position, to today's position, the position of those ice streams actually shifts around. So the ice is readjusting and the flow off the ice sheet is readjusting through that period. And if those big changes happen to be on pieces of rock, terrains that could have distinctive rock types or isotopic compositions or magnetic characteristics, we might be able to actually reconstruct from offshore that history of what's going on the ice sheet. So that's the ultimate goal. We're never going to be able to come up with something that has this level of detail, but we can weigh in on testing the hypotheses that would be predicted from this type of modeling. So this is a cartoon. I misspelled Escutia. It should be Escutia, not Escutia, from a review paper in oceanography that basically kind of sets the stage for what we're trying to do here. So this is a cross section across the continental margin, and so the basement on the bottom here, and then the subglacial sediments and the sort of wedge of sediments that were deposited from the various processes associated with glaciation. And so the ice sheet comes out to the grounding line, and then there's an ice shelf that floats above that, and ice breaks off of that margin to form icebergs. And not nearly as rich as the picture that Mike showed. I mean, I was looking at that beautiful picture from Alaska thinking, oh, too bad we can't all have that much ice rafted detritus in our icebergs. But there's, if you get too rich in ice rafted detritus, you're going to sink the berg. So maybe these are better. But anyway, a small amount of the material that was derived from these margins where the icebergs are falling off actually is incorporated in the ice deeply enough, or happens to be on the surface, happens to be able to survive as the iceberg floats out into the ocean. And when the iceberg melts, it drops its load. And Mike showed an example of what we would call a drop stone or a lone stone. That would be kind of the classic expression of that rafting of icebergs, of ice rafted detritus into the ocean. So I'm going to now show a movie, another animation, and this is from Marlo Gansworthy. Was one of the outreach people who sailed with us on Expedition 382, and she and Kevin Pluck worked together to produce generally pretty spectacular animations. But this is one that takes the observational information from satellite and I think ship observations from 1976 to near today, at least to 2019 when we had that cruise. And because we were really interested in the sediment provenance, we got them to actually colorize different parts of the Antarctic coast with different colors. So this is very schematic, but sort of to provide the visualization about what you might see in the ocean from icebergs that came off of different parts of Antarctica. So similar to what I'm going to show you in a few minutes with the age colorization of our sediment provenance, the West Antarctica is going to have this sort of pink color. Ross is going to be in the sort of red to dark pink to orangey color. Slightly, this is also going to have a lot of that same sort of 500 million years, but just to demonstrate that it might be different. And then the reason we colored this green is because there's some Grenville, like Bear Mountain up near us, in this part of Antarctica. So just to sort of emphasize the different geographic places that icebergs came from, to give a sense of, where they might end up and how you might go about working out where they came from sediment provenance studies. And remember, our cruise was over here in what's called Iceberg Alley. So you're going to see that most of the icebergs end up in what's called Iceberg Alley, which is the reason that our cruise was there, and also the reason we saw a lot of them while we were out on that cruise. But you can see that some of them actually go to different, get deposited in different parts of Antarctica. And then this Larsen B breakup really dumped so many icebergs in there. We probably ought to color it gray so that so it doesn't dominate the whole picture. But one of the things you can see is that to a reasonable first approximation, most of the icebergs don't get that far from where they started, but some of them do. So now that this is over, you can see there's a lot of green in here, not just the Larsen B, but there's a lot of green in here. But you can also see all of the other colors represented over here in Iceberg Alley. So Mike Weber was the lead proponent for the cruise that we sailed on for 382. And his sort of premise is that this is a place that captures the integrated signal of melting from the Antarctic Glacier. Ice sheets, I should say. Okay, so this is a photograph. I think these cores are from the Wilkes Land margin from Expedition 318. And the artwork is from Tina Vanderfleert. And this is just try to also recap kind of what we're trying to do, looking at the sediment grains on the ocean floor. So here we have another view of, ice stream flowing off of Antarctica, and with different geological ages shown as different colors on the continent here. And again, with the sediments flowing off from underneath the ice and from being dropped by icebergs. And here's a schematic sediment core through the sediments with a mix of local sediments and far traveled sediment. And the icebergs, the ones that are derived from this region that have the gray geology, have gray particles in them, and the ones that are derived over here from the red and green geology have red and green particles in them. And as they fall to the ocean, they drop those particles, and then we core them, take the samples, and measure their ages or other geological attributes and try to use that as a fingerprint to connect them back to where they came from. And so what I do is to use radiogenic isotopes. So these are the daughter products from long half-life radioactive isotopes, and their composition, it's essentially ages, right? Their composition is controlled by the geological age of the source. So that there's a variety of different constraints on how they get their composition, but things like when and how were they derived from the mantle, what kind of mountain building processes like metamorphism and melting and erosion and sedimentary process, other sedimentary processes and so forth. And just the fact that the variation in the geology yields this patchwork distribution of ages means that the continents, sediments derived from the continents can act as natural tracers. So what we do is to take sediments from such as those sediment cores that we have showed a couple of photographs from, and we sieve the samples. So we disaggregate them, we separate the less than 63 micron from the greater than 63 micron. 63, greater than 63 is a boundary between sand and silts and clays. So we separate the sand fraction from sand and gravel fraction from the fine grain fraction. And one of the things that we do that I'm really not going to emphasize much in this presentation, I have a little section, depending on the timing, is to look at the detrital fine grain sediments to understand their source. And we use a variety of tools, but sort of our bread and butter tool would be the neodymium isotope composition. So neodymium is a rare earth element, and one of the isotopes of neodymium is derived from another rare earth element, samarium. But what I'm going to mostly emphasize today is the hornblende argon-argon age. So argon-40 is a radiogenic daughter product of potassium-40 decay. So it's a chronometer that is fairly easy to measure, and the hornblende is a rock-forming mineral. It's not a major constituent like feldspar and quartz, but it's a common constituent of continental rocks. And it has a relatively high it represents a relatively high temperature geology. And so it's a pretty good measure of the color on the map, let's say. Wait, think I see another chat. Let me see. Is the Antarctic Peninsula connected to the Trans-Antarctic range? No, the Antarctic Peninsula is a separate mount. I think I'll have another map that shows topography again. We can look at that. Okay, so just to kind of put the, sort of the geology of the argon ages of hornblende into context, this is a figure from an introductory textbook for metamorphic rocks. So pressure or depth in the earth on the y-axis and temperature on the x-axis. And this is just the various sort of typical geothermal gradients in the earth. So the sort of normal continental, stable continental gradient, this 4 is shown here. And then mountain building, typical mountain building is shown here as collisional mountain belt. And it's not showing up so well on my diagram, but the closure temperature for hornblende, that's when the clock gets started, is about between 500 and 600 degrees. And so if you look at this graph, 500 degrees, you go down to one of the sort of typical geothermal gradients for mountain building. That puts you down at about 20 kilometers depth in the crust. And so in order to bring rocks that cool below where the clock started from 20 kilometers requires a lot of erosion. And to get that sort of level of erosion really requires the erosion from a mountain belt. So hornblende is a pretty good mineral for really kind of capturing the last major mountain building event that is on the surface, that expression of which is on the surface. Okay, so we're using sediment cores, and I'm assuming everybody knows the laws of stratigraphy, but in these sediment cores, we're taking a cylinder of sediment. And so the oldest sediment was deposited at the bottom, and the progressively younger sediments as you go up. And then we would take a sample from one of these sediment cores, sieve it like I showed you before to release the sand fraction. This is actually a fraction that's much coarser than 63 microns. Probably the sieve size was 250 microns. And then from that, we would pick hornblende grains or other grains, but we're going to really focus on hornblende for the purpose of this today's presentation. We would pick they're really black, shiny, with a notable cleavage on them. And first maybe it's sort of like, oh, how am I going to pick this out? But if it's black, it's a pretty good guess that you should look at it to think of it as hornblende. Black to green colors, and people get really used to picking them really quite quickly.
These are all disaggregated, right?
This is, yeah, so we would start with something that looks like this gray mat here, which might have, maybe as much as 10% of what we see in this picture, right? So most of this is mud that would be in the fine fraction, and a small percentage of it, in most cases, is this sand fraction. And then from this sand fraction, we would pick these hornblende grains. And you can see they all look like each other, but then when we take these and we date the individual hornblende grains, we actually see that they come from different geological terrains. So this core here, polar stern 1575, this is a X radiograph from that core. And this interval is 357 to 385. The interval that we're looking at here is from the same core, but it's a different interval that we're using as an example here. So it's not like this sample this is sort of a mixing things together, right? This sand did not come from this core, and these hornblendes may or may not have come from that sand, right? These are just sort of a collection of photographs to sort of demonstrate the strategy of the sampling and measurements. So here the hornblends are, and then here I think this is a really great example of just how much extra you get from the dating, right? Because you could count the hornblends and that would give you some important information, but getting the ages on the hornblends actually gives you even greater information. And you can see that there are distinct populations of hornblends in here. And we'll talk a little bit more about that on a map, but the Grenvillian, this circa 1 billion year old province, that's again, I mentioned about the Grenvillian in the Weddell Sea. There's several different places around Antarctica that have Grenvillian ages. And remember that this is a really, really huge major mountain belt that is found in most continents, and right near New York City, the Fordham Gneiss is Grenvillian, and the Bear Mountains. So we have Grenvillian really close to us. And then this Ross Pan-African ages around here in the sort of circa 500 million year range. And really hard to find a sediment sample around Antarctica that doesn't have a little helping of this in it. And then this younger pink here is mostly something that we would expect to find on the West Antarctica side, which I'll show before. And then the other thing that I really want to sort of use this graphic to introduce is, instead of these histograms are a really nice way of actually looking at the number of grains and kind of what age ranges they fall into. And by the way, the color scales are going to be the same color scales throughout the entire presentation. But we're going to use these pie charts, right? So these same data that are shown on this histogram are collected here in this pie chart. And what you lose from the pie chart, of course, without writing a number up there, is the number of grains that are represented. So this will be the proportion of grains that are from the 500 million year age range, but you aren't sure, just looking at the pie, how many grains went into making this this distribution of grains. And you can kind of tell by how many pieces of the pie there are, if there was a lot of grains versus not very many. And I'll just be upfront about it. Not every sample yields a lot of hornblende grains. So in some cases, maybe we'll have 3 or 4 or 5 hornblende grains instead of 50 or 60 or whatever we'd like to have in our sample. Okay, so this map is close to the latest, not quite the latest compilation of the survey of hornblende ages that we have from around Antarctica. And this slide was put together by Trevor Williams. And it's really based on two major efforts from former graduate student Elizabeth Pierce, who was a student with me at Columbia, and Patrick Simoes Perea, who was a student at Imperial College of London with Tina van der Vliert. So Elizabeth did a major effort around East Antarctica. And there's compilations from studies that predated her thesis, but she did a really major effort to sort of compile the distribution of different hornblende ages around East Antarctica. And Patrick did a very similar thing in West Antarctica. And on this slideshow that Mike will make available to you on the notes section, I actually included the references for the papers that went into the compilation that's shown here. But this is really kind of an important map for the purposes of using hornblends to trace sediment sources. So I'm going to spend a little bit of time on it. Again, this is the color scale that we're going to keep with the entire presentation. The young ages are down in the sort of light pink to dark pink interval. And you can see that they're strongly concentrated over here in West Antarctica. And Mike, to answer your question about the Trans-Antarctic Mountains, they go along, and it's hard to know exactly what you would call the extension, but the Thomas Hills, these sort of mountains over here on the east side of the Weddell Sea would be a more natural extension to the Trans-Antarctic Mountains. And then the Antarctic Peninsula, this West Antarctica, is actually an active continental, more like an arc kind of situation on the west side of Antarctica. Okay, so in East Antarctica, I mentioned that this part of Antarctica, the Wilkes-Adélie Land margin, was adjacent to Australia and has the oldest ages. And so you can see these dark blue to turquoise ages, the pies are much more concentrated over in this region. The red to orangey colors are the Ross Pan-African, and you can see there's a lot of that associated with the Trans-Antarctic Mountains. You can see that the Ross Sea is a real mix between the pinks and the red oranges, and you can see that you can't see it as well with the Weddell Sea. We'll come back to, we don't have as much data along the east side of the Antarctic Peninsula as it would be most desirable to have. But you can see that around most of East Antarctica, there's a lot of the sort of reds and oranges for the Ross Pan-African ages. These black pieces of pie here are from what's called the Groenhoogna terrain, which is a 3 billion year old province. This is part of the connection to South Africa. And then this greenish color, I don't know whether Trevor did it on purpose, but the greenish color is Grenvillian ages. So you can see that there's a decent amount of green here on the in the Weddell Sea area, Coates Land margin. And there's a little bit of green over in Pritz Bay and even in this this part of the Wilkesland coast. Okay, so this is just to say that if we look at sediment cores that are really close to Antarctica, this is essentially a core top survey, the cores offshore do a pretty good job of mapping what's known from the sparse exposures of geology onshore. And so then sort of the next thing we want to think about is, how icebergs move. And I showed that movie of the observation since 1976. This is a modeling exercise. And these different classes or different sizes of icebergs. And so you can see that the larger the big class, bigger the class, the greater the length of the spaghetti on this. So that if a big iceberg can survive and therefore travel farther than a small iceberg, all other things being equal. The things that are going to control how far an iceberg can make it are the currents that it gets into, the temperature of the water that it's in, the size of the iceberg to begin with, and then in terms of how that's expressed in the marine sediments, also the concentration of sediment in the ice is going to be an important factor. Oh, and I should say, and another really important factor is how vigorously icebergs are being sloughed off the margin, that's sending them into the ocean. And so this is an example of connecting observations of sediment provenance to modeling of iceberg movements. This is from a former student of Tina Vanderfleet, Karis Cook. And so what's shown here is pie diagrams with the same scale that we looked at before. And you can see, again, the sort of more blue and turquoise colors from the Wilkesland margin, and the more sort of orangey colors with a little bit of green in there from the Pritz Bay embayment area. And so what Karis and her colleagues did was to compare the predicted ages of hornblende grains in these four cores that just popped up, 1, 2, 3, 4, and what's seen versus what's modeled. And so you can see that actually the model does a pretty good job of estimating what you should expect to see in the sediment core. So this is the relative abundance of Wilkes Land. So the currents are flowing from Wilkes Land towards Fritz Bay. This is the relative abundance of Wilkes Land, ice-rafted detritus, and modeled icebergs. So core 1, you can see here's core 1, has a very small fraction of Wilkes Land. It's close to the continental margin, close to the Fritz Bay sources, and so it's going to have less from the more distal sources. Core 2 has a little bit more from Wilkes Land. It's a little bit farther away from the continent, and with closer within the currents more. ODP site 1165 has actually a fairly substantial amount of Wilkes Land detritus, up to say 20% of the hornblendes. And then this core number 4, farther out, actually goes back to having fewer of these because of the way that the icebergs are traveling as they come from Wilkes Land, right? So you can sort of imagine that over time, things could change, right? The number of icebergs coming from Wilkes Land could change. The number of icebergs coming from Fritz Bay could change. The exact position of the currents that are bringing the icebergs might change with differences in the temperature contrast and the wind patterns and so forth. So there's a number of moving parts that could change to change the distributions of these. But the iceberg models do a pretty good job of predicting what we actually see from these 4 cores off of Fritz Bay. And ODP 1165, the beauty of IODP cores is that they are much deeper in the sediment pile, and therefore much farther back in time. And so we've got a number of studies about the icebergs from former icebergs from 1165. So this is to build up to a little mini exercise that I'm hoping that we can sort of think through together. This is observations of the number of hornblende grains per gram in the 150 to 150 micron to 1 millimeter size fraction, shown here on this top diagram. And the second diagram is the percentage of hornblendes that are 1,400 to 1,550 million, so the Wilkes Land provenance. And then the third diagram is the neodymium. So I said I wasn't going to say too much about that, but the neodymium isotope composition of the fine grain fractions. So this is this ranges from -18 to -6. The higher the number, the less negative the number, the younger the source. The more negative, the older the source. And then this is the class greater than 1 millimeter per 10 centimeters. And so you can see that there are these intervals with relatively high concentrations of pebbles. We call these pebble burst intervals. And so this set of diagrams on the left-hand side here is from site U1356, which is off the Wilkes Land margin. And we're going to be looking at some pebbles that actually came from, we're going to look at the dates from pebbles that are found over here in 1165 over on the Fritz Bay margin. And so these are actually, Elizabeth wanted to do the same thing on the Fritz Bay margin as she did here, to sort of look at the abundance of sand grain, abundance of hornblendes in the sand grains, and separate it out and basically do the same kind of exercise as she did here. And one of the punchlines from the observations was there's no sand. There's abundant visible drop stones, but when she did the sieving, basically no sand to be found. But this is kind of a little bit of a gallery of the pebbles that were recovered from her exercise. I think these are actually probably glacial grooves on this pebble here. But you can see it's a variety of different sizes and shapes of pebbles. And so for the ones that had hornblende in them, we broke them up and measured the hornblendes ages. And so this graphic here is the ages that we found from those. And so what I'm going to do here is to stop the share. And then I'm going to pick up that table and drop it into the drop box. I mean, the chat box. There's probably a less laborious way to do this, but I can't think of how to do it. Our El Tannen and Robert Conrad, yes. Sorry, I'm not seeing these chats when they come. Y'all should just be shouting. Now, why won't it let me paste this?
Just for everyone's information, the El Tannen and Robert Conrad were former Columbia ships. But unlike the Joyous Resolution, they didn't use drilling. They used what was called piston coring.
Yeah, so they didn't get back as far in time. All right, so I'm going to have to try to save it as a file.
Sid, at some point, send it to me and I'll try to work out next activity based on what you're doing
Okay.
on the website.
Okay, let's see. All right, I'm going to try to attach. I'm going to try that. Okay, that sheet that I just showed you should now be attached as a docx file. And I apologize. I sort of came up with this morning, found the data file in a PDF, but not in a Excel file. Unfortunately, it came from an Excel file, but it's not a very large number of grains. And so I'm hoping that what you'll do now, that the activity, the sort of break from listening to me drone on, is to look at the dates from that table, look at the map, which I'm going to put up now. I'm going to come back and put up that map so you have it in front of you, and then maybe take 5 minutes or something like that, and then let's come back and discuss what we think those dates in the pebbles tell us about the where they came from. So hold on just a second. I'm going to go back to the, no, that's not it. It's brutal. Hold on, gotta find my PowerPoint again. Put something that's really distinctive up so I can see it. I have too many things open. Surprised my laptop hadn't yet spit on me. All right, we're going to put this map up while we consider the ages from those pebbles. So there's pebbles. So just to sort of emphasize, those pebbles come from over here in, doesn't show up as well as I would like for it to. Let me. The star here is the location of site 1165.
Sid, does the fact that there's appear to be no IRD in between those time periods where there were blips, meaning that there was very little movement?
Well, yeah, that's a good question. So yeah, I should say something about, I should actually kind of clarify. Yes, there's things about the sort of movement of the ice, the position of the ice, the movement of the ice, and how capable the ice is of actually picking up sediment that are, so the really cold based ice has a harder time picking up sediment, moving fast and picking up sediment. So the presence of icebergs with ice rafted detritus in them, it requires not like totally special circumstance, but a relatively special circumstance. I kind of got sidetracked answering your question, and I'm not positive I actually ended up answering it. Can you say it one more time?
Yeah, in the time periods when there was very little hornblende and other IRDs,
Yep.
does that mean there was very little ice rafting?
Yes, it either means there was very little ice rafting, or that that the water temperatures were high enough that the icebergs melted too fast to get the icebergs at the ice rafted detritus far enough out into the ocean. And the other thing that I should say, and that Trevor always emphasizes, and I think it's kind of an important thing to keep in mind, is that ice rafted detritus is enhanced around Antarctica during times of change, right? It's typically associated with warming, that you get sort of rapid movement of the glaciers and discharges of icebergs. So when the ice sheet is at its maximum extent, it may not be a very great ice rafted detritus producer. But as it's growing, as it's sort of reaching its maximum extent, it's likely to be a decent source of icebergs. And even more importantly, when it's retreating from its maximum extent, when it's like dying, decaying, is when it's really dumping icebergs into the ocean. And we sort of know this from a couple of indirect lines of evidence. One of them is just looking at the last glacial cycle, right? We have evidence from on land for kind of when Antarctica started warming up and the ice sheet started going back. And we can connect that to the sediment composition in the ocean. So when it's relatively warm, the sediment composition is really dominant, it has a really high concentration of diatoms in it. Basically, just almost the really high fraction of the entire sediment will be diatoms. And when it's colder, there'll be a lot higher proportion of the terrigenous. So we have this sort of simple lithological variability that guides us to whether it's warm versus cold conditions. And it's within the intervals that are connected to warm conditions that we tend to have a greater amount of ice rafted detritus near the continent. As you go farther out, the story kind of flip-flops, because in that case, it has to do with how cold the waters were and the survivability of the icebergs, right? So that's why it's kind of a hard question to answer, because it depends a little bit on the details of where you are. But right here where we are in 1165, the expectation would be that if we find iceberg droppings, there was a significant increase in the occurrence of icebergs.
Okay, thank you.
Okay, so who wants to weigh in on we looked at this in terms of for 1165, we looked at let me just go back to what we looked at, and I guess it was this one. For 1165, today, modern icebergs, modern observations, we have about 20% of the hornblendes are derived from the Wilkes Land margin. So what did y'all get for a proportion in these pebble bursts that were derived from the Wilkes Land margin? I guess nobody wants to speak up, or is it me? Can y'all hear me? I think I have to unshare again.
I think there's a new way for many people to look at the data.
Yeah, that's why I realized that, you know, as I was going through, I was just showing things, and I was like, if we just take a few minutes to actually, you know, sort of look at this and think about it together, I feel like it might actually make the rest of what I'm saying much more transparent. Okay, so let me try sharing one more time. I somehow got it to myself that I couldn't see the PowerPoint anymore. I mean, I couldn't see y'all anymore. No, that's the wrong one. That's just the it's just the one slide that I pulled out. So one thing that we could do to, you know, sort of like think through this is to decide what color we would make each of these entries in here, right? So if the thermochronological age is 1106, 1106 is turquoise, right? So turquoise comes from here. If the age is 513, oh, here's a map right here. If the age is 513, this doesn't show up as well, but 513 is in the red orange, right? So that probably is a locally derived iceberg. You know, it could come from much farther away. So here we go: turquoise, orange, turquoise, turquoise, orange, turquoise, 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 orange, turquoise, 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 orange, orange, turquoise, orange, turquoise, 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 orange, dark blue, orange, orange, turquoise, orange, 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 orange. Roughly speaking, something like 50% of the pebbles were derived from the Wilkes Land margin. And remembering today, something like 20% of those are coming from the Wilkes Land margin. So the interpretation that we have for that is that there were many more icebergs coming from the Wilkes Land margin during the time of this visit. We call this the Pebble burst. Well, I should have shown more pictures from the cores, but Mike showed a picture of a lone stone in a core. This is a place where, relative to the whole rest of the section, from you know, today back to the beginning of Antarctic glaciation, this interval about 14 million years ago is where you actually see the most abundant pebbles in the cores. And where you see the most abundant pebbles in the cores, here at 1165, about half of those pebbles came from, you know, more than 1,000 kilometers away, right? So suggesting that there was probably a pretty significant increase in the number of icebergs that are coming from this Wilkes Land margin. So here on the right side of this diagram, there's 1165 again. This is pie diagrams from 4 different intervals of relatively high ice rafted detritus. And so this is really close to the time of the pebbles, but so you can see that, you know, ambient background composition in that interval is still very much dominated by relatively local sources.
I think what would have helped here is if it had been resorted by age, this table, because then it's more apparent of what was going on. That's the problem.
Okay, sorry about that. I mean, ideally I would have dug it up early enough that I could find my actual Excel sheet so you could sort and look at it in different ways. But yeah. So, but now that we've sort of gone through it and looked at it from these ages, does this make it more clear, the strategy that we're taking for looking at the sediment sources?
Yeah.
Okay, cool. Are there any other questions or comments before we move on?
Hi, Sydney. I just have, I'm looking at your map here.
Yeah,
I noticed that I see there are two ocean currents. We have the polar current and the Antarctic circumpolar current.
yeah.
So if we're getting pebbles and cobbles that have provenance from Wilkes Land, I guess can that serve as a proxy or tell us something about how currents are traveling around Antarctica at the time that the sediment was deposited?
Thank you so much for asking that question. It does make me realize that I didn't emphasize a really important thing, which is that polar current. So most of the, we can go back and look at the movie, most of the icebergs that are falling off of Antarctica are being carried around Antarctica in a counterclockwise direction by the polar current. And some of them shoot off into the Antarctic circumpolar current, but they don't tend to last very long there. And so virtually it's a really, really good first order approximation that the counterclockwise motion is the one that's carrying the icebergs that we're seeing around Antarctica.
Thank you.
No,
Do you know anything about temperatures in these currents?
I mean, they're really cold. Is that what you're asking?
Yeah, there's not a difference, not a major difference about.
Oh yeah, between the polar current will be much colder than the Antarctic circumpolar current. But by the time the icebergs, if they get into the Antarctic circumpolar current, they're going to start melting pretty quickly. They're gonna not make it very far.
Okay, good. Any other observations from people?
Sidney,
Yes.
I have one question. During times of warming, when there's more ice rafted debris, is it okay to assume that subglacial drainages are also making headway continentward, or in other words, are they able to make ground the drainages at the interface? Do they cut across different lithologies eventually and expose maybe something a little different or a little new? And
Yep.
there might be the appearance of, say, an Archean chert cobble where there was Proterozoic,
Right.
or something like that.
Yes, absolutely. Really good point, Philip. Really, really good point. And it seems like it's so weird. Maybe I'm not talking as fast as usual, but I think I'm not necessarily going to get to it, but it's in this PowerPoint, an example of just that from the Wilkes Land margin. Looking at the fine-grained sediment sources, we actually see evidence for tapping into
Yes,
the deeper interior sources during warm times.
absolutely. Okay. Very neat.
Okay, so but from these pebbles, this is sort of how I would kind of illustrate the results. This is the pebble counts from the core from 1165, and then on the top is basically just in its place in the core the age of the pebble based on the 4039. And so what you can see is that there's a decent number of locally derived Pritt space sector ages. And then there's also a really quite substantial proportion of far traveled hornblende grains. And so the conclusion that we would make is that this middle Miocene climate transition has large increases in pebbles, with something on the order of 50% of the pebbles coming from the Wilkes Land margin, and probably representing substantial iceberg spalling of probably large icebergs, because they survive better, coming off of the Wilkes Land margin during that time. And then kind of coming back to this from sort of an iceberg modeling perspective, the diagram on the left is modeled iceberg tracks for today, and you can see it looks pretty similar to the set of observations that I showed the animation for. And then on the right side is a model to actually try to characterize what we see in site 1165. And for about half of the ice rafted detritus to be exotically derived, the easiest way to do that, there may be alternative interpretations, but the best interpretation that we can come up with is that there must have been many more large icebergs being derived from this Wilkes Land margin. And if you recall back to the diagrams that I showed with the sub-sea level elevations, there's these basins in here that have in the catchments that have elevations that are significantly below sea level. So this is just another example showing glaciers derived from or icebergs derived from this region, kind of where they would go in terms of the meltwater flux. So this is basically in pre-industrial times, kind of modern sort of survivability of icebergs and how much meltwater they would add to the ocean. And on the right side is a model taking the temperatures to 8 degrees above pre-industrial to sort of see how much more quickly the ice is going to melt near its source. So the time that we were just looking at is the middle Miocene climate transition. And this graph is like the one that Mike showed in the introduction with the sort of recap of what we know about the climate of the last of the Cenozoic. And this comes from the Zakos et al. Paper. And this is really one of the huge testaments to the IODP program, that we have this kind of really detailed record of what happened to climate through the Cenozoic. And the time that we're looking at here is, so Mike pointed out about the rapid glaciation, the continuation with glaciation, and then sort of a bit of a melt back. And then there's this reglaciation coming into the middle Miocene. And so this pebble burst interval that we were looking at is really close to this transition between the sort of warmer times in the earlier Miocene and the transition to colder times. And, you know, since that transition, there's a general tendency, I think it's in question now, but there's a general tendency to assume that Antarctica's had pretty much permanent ice since then. So there are fluctuations on the margins, but that the continent's been pretty thoroughly glaciated since the middle Miocene. And I'm going to skip past these fast because I want to show a little bit from Expedition 382, but Karis Cook and Trevor Williams both have put some time into this. Trevor Williams did the first paper where he looked at those 3 ages that I showed you before. You can see their little elevations in the percentage of coarse sediments at 1165, and that is from intervals of significant sort of known changes in climate. So the green arrow here, the red arrow here, and the black arrow correspond to those times on that map. And then this is the hornblende, that sort of bulk hornblende ice rafted detritus from those intervals. So the sort of ambient background is like today. It's mostly derived from the Pritz Bay sector. So this is the sort of compilation from the Pritz Bay sector on the bottom graph, and the values that are measured in the hornblendes on the top graph. Same thing, this is the Wilkes Land sector, and then this is the values that are measured at 3.5 million and 7 million years ago. And you can see there's still plenty of this Pritz Bay sector composition, but there's a big increase in the exotic materials coming from Wilkes Land. And then at this 4.8 million, we haven't seen it again. There's this really anomalous Adelie land, this sort of 1.5 billion year old source coming in here. And then these little targets in the middle here are, so the bottom is the reference provenance, the top is the data from the sediment cores, and the middle is the inferred locations where the detritus came from. So the red, this is the Pritz Bay sector, This is the Wilkes Land sector, and then the Adelie Land sector that has this 1.5 billion year age is located right here. So there's a lot more that could be done with this, but there's some really pretty cool evidence coming out of increases in the abundance of Wilkes Land sediments to 1165. And this is just to kind of give a artist rendition of those results. So this is from Trevor, the great artist. So this is the Adelie Land fingerprint, 1.5 billion year sources here. And he's showing that in this dark blue that's, you know, the color on this chart from that age range. And in order to get those up here to 1165 would require a great increase in the number of icebergs coming from there. And most of them are following along the counterclockwise polar current track, but some of them would be spinning out into the Antarctic circumpolar current. And then there's some icebergs probably always coming from Wilkes Land and from Pritz Bay, and might be mixing in. And you can see here that we have a substantial amount from Pritz Bay, you know, a smattering from this sort of intermediate ages, but then a really substantial peak from this far traveled source. And then for the 3.5 million and 7 million year samples, there's probably still icebergs coming off of Adelie Land, but we're not seeing very much of that signal over at Pritz Bay, but we're seeing a really pretty substantial signal from this Wilkes Land margin over here at 1165 in that interval. So probably a lot more icebergs coming off of the Wilkes Land margin following the counterclockwise current, some of them spinning off into the Antarctic circumpolar current. And then this is a follow-up from Karis Cook. So again, the same thermal chronological age. This is basically a lot of samples going through the interval from about 4.7 million to 2.65 million. And you can see that it's a variability between mostly local sources. So there's a lot of far travel sources in all of these, but the upper part of this diagram has a lot more of the blue in it than the bottom part of the diagram. And this boundary at about 3.2 million years is where we shift from having less than 50% coming from Wilkes Land to 50% or even more coming from Wilkes Land in that site. And this is also the time where we change from a relatively warm early Pliocene interval to a cooler and much more variable late Pliocene interval. So there's, you know, by picking these things apart and really looking in detail at where the sand grains are coming from, we can start to make some important inferences about the glacial history associated with these times of climate variability. So I think I'm running short enough of time that I'm just going to skip past this, but somebody asked about Philip, I think, asked about the local sources changing. And this section is the one you're going to want to look at for that question. The solid symbols versus the open symbols, or from the warm times versus the cold times. Said it backwards. Solid circles are from cold times. The open diamonds are from warm times. And this is basically a story of the ice sheet retreating back. And I just want to emphasize again the low elevation in this Wilkes Adelie Land region that would account for the possibility of there being a more dynamic ice sheet in there. And this is just basically sort of reconstructing what the ice sheet did. But I want to say just a couple of things about Expedition 382. I know that you talked about it a little bit already before in another session, but I don't know if everybody comes to all of them. And Mike showed the picture of Mike Weber and Mo Ramo and Trevor Williams. There was an extra site that Vicki Peck led. So the ones over here by the Falkland Islands are led by Vicki Peck. And again, this is the model that I showed you before about the iceberg trajectories today, depending on the size of the icebergs. And this is a core from within the wet LC. And this is the percentage of radiolarians. So the higher the percentage of radiolarians, the sort of warmer conditions there are. And then this is the ice rafted detritus. So you can see that there's a good correspondence between the abundance of ice rafted detritus and the evidence for sort of warmer times in this site. And this is we looked at the recovery ice stream in that video. This is a sort of a close in of the flow of the ice from the Antarctic continent into the wet LC. And we've been working along with Kathy Licht and Stephanie Brockfeld. We've been working on developing a good background of what the composition of sediments coming out of these ice streams in the wet LC would look like. And we've done a first step at looking at the sort of down core, the history of changes in this polar stern 1575. That reminds me, Mike, you brought up about the Conrad and Vima cores. A lot of these are L-tannin or IWSOE, which it stands for an expedition, and I don't know what ship that was. Stephanie probably would. And then a lot of that comes from the Palmer, I think. A lot of the cores, most of the cores that we studied that weren't IODP cores came from the Florida core repository rather than the Lamont repository, because there aren't all that many from Lamont around Antarctica. Anyway, this is the down core record. So this is the last interglacial, the previous one, the one before that. We can see that there's a substantial amount of 500 million year old hornblendes in all of these. And we can see that there's a variable amount of this 1 billion year, the Grenville stuff in there. The thing that really kind of starts standing out is the pink, the sort of details of the distribution of the pink grains in here from the young grains that are more typically from West Antarctica. And I'm not going to say more about the biotites. We've also done a lot of measurements of the biotites, but I'm going to try to focus this on the hornblendes for now. Although this is biotite, and this is zooming in, looking at the different troughs that are coming into the wet LC and the composition of the grains that we see in this in the last interglacial from the site. And basically the punchline is that there's a rather distinctive signature in this young part of the population of grains. And so there's pink in all of these, but the pink peak in this core is actually noticeably younger than the pink peak in our troughs that are coming into the wet LC from the East Antarctica side. And so this brings us to why would that be, right? They look more like the ages that you would find over here on the western side of Antarctica. And remember, I noted earlier that we really don't have a very large amount of information from this eastern side of West Antarctica. But this is a map that shows one possible configuration of the ice sheet during this warm time. And you can see that the ice is basically sort of eroded back. So there's actually even an open seaway between the wet LC and the Amundsen Sea here. And so that would leave these rocks that you can see from this map are pink. That would leave those rocks exposed to possibly being able to spall sediments off into the wet LC area. And this is I'm going to show you a example of one big dropstone from this Dove Basin part of our Expedition 382 site. But these are the cores we drilled. We got back to as much as, actually in one site, we actually tapped into 12 million years, but mostly we didn't get back past more like 5 or 6 million years during this site. And then this is from site 1536, from the early Pliocene part of 1536. And this big sandstone here is a clast. It's a dropstone that was actually so big that it got cored like the core. And this is a picture of a sandstone from the polar rock repository from outcrops on land that I think you can see looks fairly similar to that one. And then we had a student, that sandstone's called the Wyatt Earp Formation. It's from the Ellsworth Mountains from the crash site group. And we had a student from Kathy's group at IUPUI who studied the uranium-lead zircon ages. So that's a little bit like what we've been talking about with argon, but it's a different mineral, different chronometer. And you can see that there's a really pretty stunning match between the age distributions from this sample from the Polar Rock Repository and the drop stone that Connor Watkins did the analyses at this workshop on. And that basically is consistent with this really reduced extent of the ice and the possibility of icebergs coming from this really interior part. And for comparison, here's a map that's basically today, not a high resolution map, but from today, showing the location of samples from the crash site group. And you can see that there's a huge amount of ice between this location and the ocean today. But if the ice were greatly retreated, like in this model, then the Ellsworth Mountains would be right there available to be dropping icebergs with that composition out into the ocean. And then one last thing, I was going to have another like think about it, but I think we're probably out of time for that. But this is along that same the most recent last interglacial, and this is samples that we took based on the ice rafted detritus abundance, and we took the one with the most abundant sediment sand in it and made some ages. So this is a plot of age of the hornblende grain against rank. So the youngest one's going to be 1 and the oldest one's going to be 32 or whatever, however many grains I was able to get out of there. And so you can see that there's a really strong population that's in this sort of 100 million year range. There's a few in between, and then there's a big population in this 500 million year range. And then there's another population that's in this 1 billion year range. And then there's this one lone grain over here at 3 billion. So I said, let's think about these data, time permitting, and Mike can tell me if I'm wrong. I see I have a chat, so let me look at that right now. IWSOE was on the Coast Guard Cutter Glacier. Mary, exotically derived means it came from far away. Yes, exotic means far away. And the sediment sources do give insights on how long the icebergs survive. But I think they also, I think in order for them to get there, there have to be abundant icebergs, right? They kind of, but their melting kind of makes the water colder and makes them last longer. But, one lonely iceberg probably wouldn't make it that far, even if it's pretty big. Okay. So let's think about these data. I was going to put up put a PowerPoint in the chat and have you look at them like before, but sort of let's just instead take it through together. So here's that map again with all the colors in it, and the in the teeny little diagram that I'm going by memory because I can't see here, so I guess you probably can't either. Down here in the very young ages is the pink, right? So 100 million down here in the young ages, and the pink is over here in West Antarctica, right? So these ages that are below, say 150 or 200 million years are likely derived from the West Antarctica part of this map, okay? And then here we go. We got this population that's about 500 million years. And remember, this 500 million year population is in sort of red-orange color. So we've got Ross in the red, and then the green, this 1 billion year is coming from Grenville sources. And then this one grain over here would be in this black area. So it would be coming from Grunhogna. So if you remember how the currents are flowing, they come counterclockwise around Antarctica, into the Weddell Sea and then go sweeping out into the Antarctic circumpolar current. So some of them sweep out before they get here, but the real pattern is they come around, they come through, and they sweep out. So we're kind of collecting icebergs from all of the Weddell Sea, and possibly we're collecting some that are flowing directly from over here on the west side of Antarctica, possibly making their way all the way around, or possibly kind of spinning out into the Antarctic circumpolar current earlier, or possibly because of the ice being retreated greatly in here, actually tapping in to West Antarctica on the east side of the Antarctic Peninsula. So just because I sort of build this as about IODP, this is from a recent review article by Carlotta Escuccia and others, and it shows as of 2019, it shows sort of both the past drill sites from IODP and the upcoming sites. That includes 382, right, 379. All these basically have now been completed, and then there's more upcoming proposals for drilling further, getting further information from Antarctica. But you can see that there's already been a really pretty impressive sort of success at tapping into the history around Antarctica with IODP, and it's just sort of the tip of the iceberg, I guess, pun intended, because it's a really kind of an important way of understanding the past and using that to kind of predict the future. So the geology of the subglacial bedrock provides natural sediment tracers. Several examples show evidence of past dramatic ice sheet activity in East Antarctic sectors. And one of the things we'd really like to know, and hopefully we can learn as a result of these new expeditions, including our own to the Iceberg Alley, is how did Antarctica's ice change through the intervals of time in the Cenozoic, those big climate changes that are demonstrated in the Zakos curve for the oxygen isotopes, and specifically in our site in 382, we essentially have a south to north transect in cores from that polar stern core I show you, as well as cores from the 382 cruise, where we can actually look at whether the terminations have the same sources as each other, or whether there's some variation with latitude in what they capture from the icebergs coming off of Antarctica, which should tell us something more about how the icebergs are moving back in the past times.
Thanks very much, Sid.
Yes.
You and I will
Thank
work
you.
online through emails to try to get some of the information onto the website so we can develop some activities.
Okay, great. Yeah, that would be great. Actually, I would very much appreciate. I appreciate the comments I've already gotten, but I would also appreciate any insights about how to use this to develop sort of activities that don't take too long, but could actually lead to furthering the understanding of the application.
We'll try to work on that. I'll bring some of the other teachers in on that. I know Renee likes to do things like this.
Yeah, I thank you. I mean, I think that would be, I feel like it's so much more empowering to actually be able to sort of look at data and say, okay, or question it, right? I was actually I guess Philip kind of touched on the one thing I was kind of expecting was, how do you know it's being carried by the icebergs? Why couldn't you have just tapped deeper into the Antarctic ice sheet? The rocks are not well exposed, and so these are not illegitimate questions whether you might be able to do that. So I just sort of think being able to kind of like look at what information is available and the data and think about, what are the most likely reasons for the observations you see. Would be a really kind of fun type of activity.
Okay, I'll bring an open invitation to everybody who's here to help us with that. Any other questions?
I have one if it's okay.
Yes, Philip.
What happens to the warm period diatoms and the warm period radiolera? Do they are they analyzed for age dates for comparison, or are they in the state where they're no longer of any taxonomic value?
No, in many cases, they're really quite beautifully preserved. I mean, it's variable. It's variable how well preserved they are, but they're one of the, that was our biostratigraphy from 382 was largely from the diatom and radiolarian taxa.
I see.
So as you might be aware, there's lots of things that can be, we learned a lot about from the lectures from the specialists while we were on the cruise about all the different things that you can do with these organisms, right? Not only are they good for biostratigraphy, which is incredibly valuable, but they're also very important for environmental interpretations, right? So they use them for the presence or absence of sea ice, things about to do with the nutrient composition of the surface waters and so forth. So there's a lot of extra that can come out of the studies of those, and that's one of the things that we really hope to do for 382 is to put together all those kinds of lines of evidence to really understand what happened in the past.
Yes. Do you see a steady conversion of the silica with the depth of the core eventually?
Say that one more time.
Do you see a steady conversion of the diatoms and radiolera with depth and increasing age over time? Do they begin to go through their diagenesis, and do you see the changes in the skeletal structures?
So we didn't get back far enough in 382 for them to be really sort of like turned into chert kind of thing, if that's what you're asking. I think that some sites around Antarctica have gotten deep enough to get into where the silica secreting organisms have been turned into chert, but ours weren't. Now there was variability in how well preserved they were, and it was my understanding, and Stephanie might remember better, but it was my understanding that the interpretation from that was more environmental. Like in sometimes the bottom waters would be more corrosive than other times, and so in some of those intervals, the preservation was fairly bad. And I thought you were going to ask. There's also the possibility of reworking, right? These are pretty strong currents flowing around here, and so we definitely had instances where organisms that were older than the strata were in the strata, right? So they're being eroded from pre-existing strata into our sites.
Okay.
And I think that's a relatively common thing for biostratigraphers to have to deal with.
Exactly. Yes.
Okay, I had a couple of questions in the chat that I'll read. Someone asked, is there any effect of the Coriolis effect on the iceberg movements?
Yes, definitely the Coriolis would make some effect on that. And in fact, that they're sort of sweeping out into the Antarctic circumpolar current, I think would be an example of Coriolis kind of having an impact on their paths.
Another question is, diatoms and radiolarians come from warm samples. What organisms did you find in the colder samples?
Yeah, so that's a good question. We actually found, I don't think there was a single sample where we didn't have abundant diatoms and radiolaria. I mean, maybe it was variable and the species composition was variable, but we found those organisms basically in all the samples. But the proportion, the relative bulk concentration relative to the full sediment was higher in warm times. So there's just more flux of terrigenous clastics that kind of dilute away those organisms during the cold times.
And I know Renee wants me to ask this question. Coccolithic foridi?
You know that we did not see much carbonate, sadly. And then we did. So Vicki Peck is really quite an amazing observationalist, and she was looking through the microscope and discovered a bunch of stuff, and she found foraminifera. So not, you know, it was exciting, but you know, maybe not that many. Like she picked everyone she could find, and maybe there's going to be enough for some stable isotope analyses, but and not enough benthics, right? So she only found, I think she may have found more than one species, but it was mostly pachyderma that they found, that Vicki found in there. And I do think there was a couple of intervals down in the older part where there was limestones that looked like maybe it's sort of pre-glacial. Here, Stephanie has something. The shipboard team's looking at the microfossil assemblages and details. There are diatoms that live and thrive in sea ice. Those tend to be more abundant during cool intervals. Yeah, it really is true that just in general, we had a substantial group of diatom specialists, and their main research is not biostratigraphy. They were there because of the environmental implications of the sort of species composition. And I think there's some like shape constraints, whether they're in the sea ice or not. So there are a lot of things that they look at that give them extra information about the environmental situation.
Thank you. Any other questions? If not, I want to give a big thank you to Sid.
Thank you all for your patience.
Stay
Thank
well.
you. Thank you all for coming.